We're going to solve question 2 in our practice exam. What do you do when you hear thickness, diameter, and thin wall? So as you can guess, this is a thin wall pressure vessel problem. So giant aluminum soda can. So aluminum, so I know my Young's modulus 69 GPa. I know that my mu is equal to 0.3. I have a thickness equals 5 millimeters. I have a length, doesn't matter. I pressurize my soda can with, so my delta P is equal to 1 megapascal. My diameter, or my radius, is equal to 15 meters. I'm also given that the gauge factor for this Wheatstone bridge is 4. So my F is equal to 4. The gauge resistances are 150 kilonewtons, so I know that if they're all equal, I know that my output voltage at balance is equal to 0. So, and then it also says the excitation voltage, so VI is equal to 500 millivolts. So let's go ahead and start to plug in some of these values in our Mathematica notebook. So I'm going to go over here. So let's go right here. Let's scroll up a little bit so we can see. And then now let's go ahead. My Young's modulus, y is equal to 69 times 10 to the 9th. My nu is equal to 0.3. 0.3. My thickness is equal to 5 times 10 to the minus 3. My del P is equal to 1 times 10 to the 6 pascals. My radius is equal to 15. My F is equal to 4. My VI is equal to 500 times 10 to the minus 3. So first thing, if I hear diameter thickness, radius thickness, R over T, greater than 10, so I know I'm in thin walled pressure vessel. If I know that, I know my stress tensor. If I line my coordinate system like this, 1, 2, I know my stress tensor will be sigma L, sigma hoop, 0, 0, 0, 0, 0, 0, 0. I know that my hoop strain is equal to 1 over E, sigma H minus nu sigma L. My sigma L is equal to 1 over E times sigma L minus nu sigma H. So I could always write down those values. Now, the other question is, how are we going to, or what other information are we given? Are we given a shunt? No, so I know that I'm going to use this expression. I equals over 4 epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4. I only have one strain gauge, so these are all 0, 0, 0, 0, and my epsilon 4 is going to be equal to the hoop strain plus alpha delta T. You have to write this expression and consider the thermal contribution. However, there's no information in this problem about basically a change in temperature or an alpha. So if there's no change in temperature, this is going to be equal to 0. So we can now start to kind of solve and write out this problem. So let's go ahead and solve for some of these values. So I know my sig H is equal to LP times R divided by T. My sig L is equal to sig H divided by 2. My E sub H equals 1 over Y times sig H minus nu times sig L. And my EL is equal to 1 over Y times sig L minus nu times sig H. There we go. That's my hoop strain. That's my longitudinal strain. Those are my stress tensors. So I'm all good to go at this point. So I've written out the full stress and strain tensors quantitatively. What's the rotation to get to the principal stress state? We're already in it, so that's 0 degrees. What about maximum shear? Well, if my Mohr circle looks like this, tau here, this is sigma H, this is sigma L, this is that circle, so I'm already here. So I need to rotate a 2 theta equal to 90 to get to my maximum shear stress. So that theta is going to be equal to 45 degrees, clockwise, counterclockwise. It also says draw the 3D Mohr circle for the stress state above. Well, I already know that I'm in my principal stress state, so these are my principal stress values. So if I want to draw the Mohr circle, it's just going to be the following. So sigma H, sigma L, and here. 1, 2, 3. That'll be my 3D Mohr circle in those values. So I'll calculate the strain measured in gauge 4 quantitatively. We already know that this is equal to EH, so we've got that value. And Then finally, what's the output voltage, the Wheatstone bridge once we pressurize the soda can? Well, that's going to simply be our, so actually, we'll just F divided by 4 times EH times VI. So we can look at those units again, dimensionless volts, and that's going to be that voltage that will be our output voltage again in volts for that solution. So again, when you're doing these thin wall pressure vessel problems, hopefully again they're a little bit or fairly kind of straightforward as you go through and work through these problems. So, but yeah, that's essentially our solution for this problem. So let me know if you have any questions, and I'll be happy to kind of clarify. Thanks. Bye.